All right, so our speaker is Josh. He's currently a postdoc at the University of Minnesota, based at Fermilab. Before that, he was a postdoc with MIT, Tel Aviv, Fermilab, and did his PhD at Tennessee.
Yeah, so thanks, Tyler, and others for the invite, and hopefully can have a kind of informal discussion about machine learning applications to neutrino energy estimators. So of course, we are heading into the Dune era, and we really want to understand how we can reconstruct these in a more appropriate way to hopefully improve our understanding of oscillations. So I guess I need to click probably. Let's see. There we go. Okay, so are we all postdocs or yeah, okay. So I can probably speed through a lot of this, and then we can get to the meat of the subject.
Some of them are not in the.
Oh, sorry. You're a grad student?
No, they're not in
postdocs,
the.
but we're actually AMO postdocs.
Oh, okay. Well, awesome. I'm glad that you're far more useful than me. Okay, so weak interactions in the standard model are somewhat similar to electromagnetic interactions. We have quasi-elastic-like interactions, which are basically interactions on a single nucleon, where we have that as our degree of freedom. We can exchange a Z or a W, and this occurs with a vector minus axial vector interaction in conversion to the kind of electromagnetic scattering. Of course, this interaction on a nucleus is much more complicated by all of the other parts of the nuclear medium. We call this colloquially the internuclear cascade, or final state interactions before you get to your final state, because you can have rescattering of the struck proton, which then through charge can go through a delta and then kind of give off a pion, for instance, give you a neutron, and then the neutron propagates, and then you have lots of other stuff happening. So this is kind of the complicated vision of the nucleus that we have to deal with when we're putting together neutrino interactions in our experiments. As far as properties are concerned, we know that the neutrino doesn't have strong interactions. It's electrically neutral. It has only weak interactions. These affect the Z decay, for instance, for Z to invisibles. You can see here some data that is actually increased with error bars by a factor of 10, where we fit different models of either a 2 neutrino, 4 neutrino, or 3 neutrino paradigm. And you can see that Z to invisibles matches perfectly with the 3 neutrino. And so what this means is that we have a way of saying that there are 3 active neutrinos in these invisibles, but there's more to it than this. As you might know, in the standard model, masses of the neutrinos are expected to be 0, but you've probably also heard that there are oscillations. And of course, if you are a 0-massed object, you cannot have oscillations like flavor conversion in the standard model. So the fact that these are the active ones doesn't say anything about the sterile or the starina that we were just discussing. But in principle, you can have singlets of the standard model that do other things. So these are some of our past detectors and current detectors. We have SNO, we have Super K, and of course the Homestake detector with Ray Davis. And all of these together led to a couple of Nobel Prizes and led to the discovery of neutrino oscillations. You can see here, for instance, a beautiful image from Super K of how we do our reconstruction with Cherenkov rings coming from neutrino interactions. And of course, this led to the joint Nobel Prize between Kajita-san and Art McDonald, and then originally by Ray Davis here. All of this kind of created the paradigm of what we think of as 3-flavor mixing. So this is all encapsulated in something called the PMNS matrix, the Pontecorvo-Maki-Nakagawa-Sakata matrix. I will not say it again. And point being that you can have 3 neutrino flavor states that oscillate via 3 eigenstates. So a way of kind of encapsulating this is that you have nu3, nu2, and nu1 that are all admixtures of different colors here, which represent our different flavors. And then you can look at those as a function of what happens with what's called delta CP. So delta CP is one particular parameter in the PMNS matrix, and you can see that basically our uncertainty on that parameter leads to different admixtures in this particular normal order. There's other orderings that are possible. You can in principle flip this on its head. You don't know which neutrino is necessarily more massive. We can encapsulate these two in mass splittings called the atmospheric mass splitting and the solar mass splitting, which are very small. And in principle, nu1 can be zero massed in principle. So all of this is said that the mass splitting is calculated this way between the different flavors. And these mass splittings are, of course, are not exactly precisely known, and the ordering is not known. But we hope to directly test that with our interferometry, basically, our oscillation experiments. And then, of course, delta CP here might play a role in leptogenesis, which is a particular way at high scales of developing a matter-antimatter asymmetry in the early universe. May help do that if neutrinos are also Majorana. But this is a central motivator, this particular measurement of the work that I'll present today. Putting this all together in a two-flavor paradigm. So this is an approximation. Is there a question?
Oh, no, just
Okay. Point being that, oh, sorry. Hi, Eye of Sauron. Point being that you can put this into a two-flavor paradigm. You can look at how basically the amplitude here is mediated by this mixing angle. And then we have the period mediated by the period mediated by delta M squared. So that's that mass splitting. And then L over E is our dynamical parameter here, basically showing the oscillations as a function of distance over energy. So point being here that you can use the three-flavor paradigm to get this, but of course the oscillations to nu E are very, very tiny. So this allows you in principle to kind of have like a more of a two-flavor ideal, where I'm going from mostly muon to tau. The problem being, of course, that you don't necessarily produce taus on shell in this way. Okay, so how do we produce neutrinos? We first, of course, start with protons, for instance, at Fermilab at the accelerator division. We go through different targetry. You basically hit things like beryllium or graphite or other things that you can spallate on, and then produce a lot of pions. Those pions get focused by a horn, and then those pions go through either a basically vacuum vessel or very low pressure, like helium gas, and are allowed to decay inside this long hall. And then you can basically allow those pions to decay. They produce muons and then muon neutrinos. And then through here, you can track, for instance, how many muons you get that punch through, and you get some understanding of the normalization of your beam. So all of this basically goes into producing these new mu's at these proton accelerators. And then we want to, of course, in a full kind of oscillation scheme, we want to have an understanding of what those look like in a near detector before they go through these long distances at the energies that are shown here to oscillate into a different spectral pattern. So we're looking at the exact same reconstructed neutrino energy here, but you can see that we have these new imprints that are basically emblematic of these flavor changes. So I have new mu's that are basically disappearing and leading to this, this different shape over here. We have, of course, reduced interaction with the far detector due to divergencies, but in principle, we want to understand how this particular shape arises and then derive our PMNS parameters from there. There's different scattering processes that can occur here over these reconstructed neutrino energies, and depending on how complicated these processes are, whether we're dealing with deep inelastic scattering, resonant production, meson exchange or 2p2h, coherent, et cetera, neutral current processes, all of them have different uncertainties with which you want to try to reconstruct that neutrino energy in order to get back to something like a true energy in order to understand our oscillation effects. So the question is, how do you derive these reconstructed neutrino energies in as accurate a way as possible? And then, of course, we want to map that to true. And so I'll kind of play around with another quasi-elastic, like again, kind of single nucleon idea, some of these. So how do you actually reconstruct that? You have an incoming neutrino, a neutrino coming into your generally unmagnetized detector. It's going to have an unknown incoming energy. You saw that spectrum. It's not a monoenergetic beam like in an electron experiment. And then it's going to interact. And it can interact in a quasi-elastic way. What that means, right, is that it's going to interact on a single nucleon, not two nucleons, not quarks necessarily. Again, the degree of freedom is that single nucleon, that means that in principle, you can have an outgoing nucleon like a proton, and then an outgoing charged particle like a muon in the case of a charge current interaction. Now, this general is just an interaction example. There's much more complicated stuff that you can do, but this is a very simple topology that we'd like to kind of play with. And of course, the definitive initial energy is unknown. It's limited by this observable final state. There may be other stuff that's invisible here. There might be neutrons, there might be stuff below threshold in our detectors. But nevertheless, we try to understand, for instance, ionization, calorimetry, light production, all of these things, range, in order to get at what that energy of that interaction might be. And that becomes very difficult, especially if you have no magnetic curvature for either of these particles. So what we want to do eventually, right, is we want to understand this oscillated flux, okay, not necessarily the spectrum, but the actual flux. And what that means is that we have to back out what the interaction is. So of course, what happens in principle is that the neutrino comes in, it interacts with the nucleus, particles shoot out into this final state. There's all of this complicated stuff happening in the nucleus, which means that if we want to basically go in the opposite direction, we have to measure those particles, we have to apply an interaction model to kind of go backward and understand the nuclear physics that took place. And then we want to infer the neutrino flux from here. And so this is a very complicated reconstruction problem. In general, neutrino experiments are basically counting experiments. We're counting things as a function of alpha flavor, energy, and potentially baseline. So you have a reconstructed quantity here, but this is related to, of course, your incoming flux, some kind of interaction model. And then from here, you are going to integrate over that true energy. Of course, the flux here is dependent on our true incoming energy, which is dependent on if you have oscillations, for instance, a probability that is actually affecting that energy over that baseline, over that length, given some near detector constraint here, where you have oscillation parameters entering into this probability. So all of this is kind of complicated, of course, because you're mixing different aspects. You need to understand your true neutrino energy from the flux. You need to understand the cross-section, the interaction probability effectively of that occurring. And then you need a mapping function, R, that actually is able to understand how the reconstructed matches to the true in the most simple case. So an example here, right, is that you have a near detector in blue, you have a far detector in red, you have data here in principle that you would measure in your far detector, you would also measure them in a near detector, of course. And the way that we actually go about doing these kinds of experiments is we think about how we get out different aspects of theta and delta M squared given our L over E. So we have an E distribution here, but of course this is the reconstructed versus the true, there is a difference. And then we know how to measure our baseline hopefully quite well between our near and our far detector. And so what we do between the near and the far detectors is we actually take a ratio to do basically the interferometry. And that leads to this structure where you have the dip here, which is related to theta. And then you have basically a width, if you will, here, which is related to delta M squared. And this is, of course, just a two neutrino paradigm. In principle, you'd want to do this across many different flavors. You'd want to do what are called appearance experiments, disappearance experiments, appearance being where you see an electron or you see a muon, disappearance where you actually don't. Of course, the problem is how we map these back. So that's kind of what I'll be applying today. But I want to take a brief aside and say that this goes beyond just thinking about beam experiments. We have atmospheric neutrinos as well, which are coming from all around. And of course, if we have underground experiments that are very large, we'll have a significant exposure of these. So these are produced in the atmosphere through cosmic rays, where of course, through these cascades produce things like electron and muon neutrinos at approximately a 2-to-1 ratio. Now, all of these have different baselines, which is quite nice. And they all have different MSW effects because of the density profile of the Earth. And so what that means is that through a single detector, I can actually have many components of L and many components of E. So this leads to very rich, naturally rich oscillation phenomenology across a very wide range of energies. So in the sub-GeV region, maybe up to something like 2 GeV really, you have PM&S, sensitivity to delta CP. Beyond that, you have mass ordering, especially coming through the core region, through the very high density region. And then above that, where you have very high mass splittings, in principle with the stereo neutrino, you might be sensitive to those. And beyond that, we don't typically think about astrophysics, at least not in the context of our smaller detectors. So all of this kind of came into my life as a researcher after this very nice paper from Pedro Machado and Ivan Martinez Soler and Kevin Kelly back in 2019, this PRL, where they showed, I should say, very interesting sensitivities to the Dune experiment to potentially delta CP values and being able to do something like 2 to 3 sigma measurements in Dune just with atmospheric neutrinos. So I'll talk about Dune in a little bit, but Dune is a big liquid argon time projection chamber. One of the main things that it wants to measure is delta CP. And of course, there's a history now of joint measurements between experiments, and that usually takes very long periods. I think it was 20 years roughly for a beam plus atmospheric fit in Super K, for instance. And this is something that we want to start thinking about now, where we're able to actually get something like just atmospheric sensitivity of 3 sigma and integrate that into the beam for an even higher, more competitive sensitivity. So, of course, atmospherics are valuable because of this, and because Dune is capable at reconstructing low energy stuff, it has potentially excellent capability to do this. And if we add these to the beam, we can break degeneracies potentially, which actually means that it's a much more consistent measurement. Yes.
So, what you're trying to get from this plot is, I just want to make sure I fully understand.
Sure.
Is the delta actually like the delta CP?
So what this,
Yes, right? That's a delta CP, yes, okay.
yeah, and then this is basically sensitivity. So this is delta chi squared, which is related to like a
But
negative log likelihood.
is the idea that I guess I'm surprised that hasn't been done before, given that.
I mean, this was 2019, so it's 6 years ago.
I know, but 2019, you have a bunch of other experiments that have measured a lot of.
Sure. But a lot of them do not have low energy capability.
Okay.
So for instance, in the context of Dune, right, we're a liquid argon time projection chamber, we have very low hadronic thresholds. That means that we can reconstruct protons. That means that we can reconstruct quasi-elastic interactions. And that is not the case necessarily in Super Kamiokande, because Super Kamiokande has water Cherenkov technology, and therefore is basically unable to reproduce any kind of proton reconstruction below 1 to 1.5 GeV. So that means you're not sensitive to the same regions. Similarly,
But
if you look at,
but the 1 GeV region, then you end up having a lot of, that'd be interesting, yeah, a lot of more backgrounds from just environmentals, and ends up being kind of where.
so we have basically no backgrounds. So we're at least in Dune, in the Dune context, right? We're 5,000 feet underground. So we have cosmics, yes, but they are easily identified. They cross the detector.
Interesting. All right, thanks.
Yeah, so I have a question. So I'm trying to understand that plot. Is that saying that the region that we're most sensitive to, or Dune will be more sensitive to, for delta CP is pi over 2 to like.
This is with a given input. So what this is an exclusion, right?
Okay.
So what you should interpret this as is saying, if this happens, this is your Asimov point. If this is your true value, right? Then I can exclude at 3 sigma, so 99.4 or whatever confidence level.
Okay.
I can't remember exactly. I can exclude everything below this.
Okay, I was confusing this with the discovery sensitivity
Right,
plot.
yeah, same.
Okay,
Yeah, it's an exclusion.
got it. Thanks.
Yeah. Okay, so the question basically is, with respect to especially this region here and roughly the sub-GeV region, there's a lot of nuclear physics at play. And so we want to potentially do improvements to our not only energy reconstruction with atmospherics, but we also need the angular reconstruction because we need to know what baseline we are. We need to know where the neutrino is coming from in the earth. We need to know how much density, how much earth it saw on its way to our detector. And so that means we have to improve both of these simultaneously. And that means that we have to overcome things like Fermi motion, things like final state interactions, and get better at recognizing how to reconstruct those lower energy regimes. And that means that we need to hopefully improve these, and maybe machine learning is one aspect that can do this. So just to kind of show the full parameter space here in the three flavor paradigm, you can see electron to electron, electron to muon, electron to tau, muon to electron, muon to muon, and muon to tau oscillations. This is just probabilities. These are not fluxes. This is not, emblematic of our rates necessarily. But you can see here some structure that's interesting, potentially, particularly in our mu to E, right? So we start with mostly muons in our atmosphere. And then we are going to have muon neutrinos come out of those decays, and then they can oscillate through the Earth into electron neutrinos as a function of energy and angle, in this case of the zenith angle. So this is related directly to the baseline. What you can see, right, is that there's a lot of very fast oscillations here, but there is some kind of more globular structure that in principle allows you a certain amount of sensitivity. And what you see, right, is that mostly below something like 1 or 2 GeV here, that this globular structure is observable as a function of angle. So if I look at mostly upward going angles here, if I'm able to resolve this area and this area and this area, basically I'm not that sensitive to my energy reconstruction, but I'm very sensitive to my angular reconstruction. Similarly, if I look at kind of higher energies, particularly around, for instance, mu to mu, or electron to electron, or muon to tau, right? What I see instead is that in very upward going regimes, I have very strong oscillations across many different energies. So if I'm able to point relatively well downward, I'm able to reconstruct upward going stuff, then in principle, I can read out different areas here as a function of energy in the kind of 1 to 10 GeV range. And that allows me to do mass ordering. So improving our angular resolution is really important in the sub-GeV region. This is just an example of that. If I look at a delta CP value of pi over 2, so maximal, versus a delta CP value of 0, sorry. If I look at the difference between those two plots, I can see the absolute difference in the probabilities here. And you can see that this is very strong in this kind of sub-GeV region. But I also need to have relatively good pointing here where I'm able to kind of make these cutoffs in each case if I want to measure that. Of course, the very fast stuff I would average over effectively. I wouldn't be able to resolve that. Another way of looking at it is this here. Basically, this again is just making the point that you can make different assumptions about delta CP. It becomes kind of difficult to do these resolutions, but at these very low energies, all of this is to say is that, we really want to exploit technologies like DUNE, liquid argon time projecting chambers, to get at these hadron-rich final states in these low energy regimes. And of course, you have to contend with large systematic uncertainties, particularly not just from the flux, but also the interactions at those very kind of nuclear energy level, nuclear interaction levels of energy here. I also can look at, for instance, the mass ordering. So again, this is the ordering of nu1, nu2, or nu3. And you can see here the same kind of effect if I have the normal ordering. So if I go nu1 through nu3, or the inverted ordering, which is the opposite. And then you can see that you have lots and lots of loss of probability here in this case. So, and this is mostly in a higher energy regime, between about 2 and 10 GeV. But as you can see, there's very little angular dependence in some of these regimes.
Say again what the heat is,
About the what?
what the heat is, the color scale.
It's the absolute difference in probability of oscillation between the normal ordering minus the inverted ordering. So if I change basically my PM&S parameters and I switch 1 with 3, that gets you that.
So you have good distinguishing power in the when the absolute value of that is large and it fades.
Yes. So I mean, it's either the normal ordering or the inverted ordering, right? Like this is a smoking gun in some respect. The previous plot I showed you is kind of a lie. There is no reason that they have to be either of these things, maximal or minimal, right? This is just one example of where the effect lies in principle. But the kind of binary decision of normal ordering versus inverted ordering really gives you a very clear marker. So that's very nice for us. Okay, so just quickly going through some detectors. We of course have Hyperkami Konde coming through, and as well as Dune, which is based at Fermilab, and of course Japan. We're going to hopefully from these measure delta CP and mass ordering, and all of those are going to have first measurements that are actually going to start with atmospheric neutrinos. Especially in the context of Dune, we don't have the beam for something like 2 to 4 years. So we will have our first detectors and the FAR detectors coming online, and then we're going to be commissioning and so on and so forth, but they will be running, actually taking data for 2 to 4 years before the beam turns on. So there's a lot of physics that we in principle can start doing, including, for instance, studies of tau production, BSM physics, different non-standard interactions for neutrinos. Of course, there's calibrations and there are cross-section studies, especially in the near detector, that we can start doing eventually. But of course, that requires the beam. And of course, a favorite of mine is baryon number violation. I've talked to you, a couple of you about that. I've worked with you on that, but you can ask me later about that if you like. As we already said, there are 2 different kinds of technologies. We have water Cherenkov, we have liquid argon time projection chambers. And of course, this is kind of a battle-tested technology. We've done this for 30 or 40 years at this point. Oxygen is a really nice, quote unquote, simple symmetric nucleus. We kind of understand it. And of course, because of this, it is very easy to scale and to purify these kinds of things to make them work really well. The problem is, as I already mentioned, is that we have really high proton thresholds and we have lack of gamma and electron separation power in principle. There are some interesting ways of doing different things here, but point being that you usually have to make an assumption about the kinds of interactions that you're reconstructing, which is not necessarily the best. And this is in contrast, of course, to Dune. Okay, so we're here. We've just actually completed our excavation of 800,000 kilotons of rock. This is us here, and there's Linda, by the way, for those of you who might remember Linda Cremonese. But point being that we're at the 4910 level here at the Sanford Underground Research Facility, and we have 1,400 collaborators. To put this in perspective of how quiet this detector is expected to be in the kind of GeV regime. To put this in perspective, if you look at a number of cosmics in microboon, which is a 85-ton liquid argon time projection chamber sitting basically on the surface at Fermilab, you get roughly 4,000 cosmics per second. 5,000 feet underground, you get 4,000 cosmics per day per 10,000 tons. So you basically get less than, I think it's 5 cosmics per cubic meter per day. So it's an incredibly quiet detector. We do have radiologicals, we have other aspects there, but it's an incredibly quiet detector, which really makes the kinds of interactions that we're looking for with atmospherics very much easier, because we're looking basically for an unconnected vertex. So it's very nice. And of course, we're going to be doing this for about 2 years before beam from our atmospherics. This is what the atmospheric spectra looks like at the Homestake mine for Dune. So this is work done by Marcelo and myself way back in the day. And you can see that we have all different kinds of charge current and neutral current interactions for different flavors here. But point being that they basically all peak at around 200 to 300 MeV, so quite low energy, except for the tau spectrums over here in the charge current cases. And that's of course because taus are very heavy and you have to turn on your on threshold production. So this is much lower energy than the artificially produced beam for Dune, and that makes us, again, reconstruction very difficult. Just kind of understanding the statistics here as a function of sub-GeV, multi-GeV, and high energy, and then totals, you can see this broken down by different interaction types and flavors. In general, if you look at the sub-GeV to multi-GeV regime, so 1 to 10 GeV, we're expecting roughly 60,000 charge current interactions for our atmospherics. To put that in the context of the beam for Dune at the far detector, we're expecting tens of thousands, not 60,000. So artificially, we understand more about the beam, of course, than the atmospheric natural flux, but the statistics here is encouraging. I'll also just mention that we have some very interesting production for taus that's possible. So in our higher energy bends, right, up to 100 GeV, where we may not necessarily have containment in our detector, we still get actually quite high tau charge current rates. And if you look at just the hadronic decays, then you're talking something on the order of 200 charge current produced taus that are going to decay hadronically, which is very encouraging. That would be a world-leading set of data that has only been statistically implied from places like Super K. And this would be a technology that in principle could actually reconstruct that very interesting topology. So how does that work? We do this with liquid argon time projection chambers, as I mentioned. In contrast to Super K, Water-Cherenkov, this actually has built-in electron and gamma discrimination by looking at electron showers versus photon showers, where you have your vertices here marked in a star. If you had an actual electron production at your vertex, you immediately start ionizing the medium before showering. And similarly, or not similarly, if you have a gamma, you actually have a gap in this way, where you produce the photon and it propagates for some period of time. What that means as well is that the first several hits are actually either 1 or 2 times the minimum ionizing particle threshold, which is a nice way of being able to separate these. So the way this works, right, is we have charged particles, they enter the medium, you ionize the medium is actually held in a voltage, a high voltage. We have a electric field that drifts these electrons to sense wires. Those sense wires are angled at different ways, about 120 degrees, 60 degrees to each other. And then you can actually get projections of these wire planes that allow you to do 3-dimensional reconstruction by combining the views. All of this is encouraged further because liquid argon has really low thresholds, especially for those hadrons, inaccessible for Water-Cherenkov. And of course, there's lots of working examples of these. The problem, of course, is that argon is a lot more complicated than oxygen. And we have a lot more neutrons, a lot more protons, a lot more nuclear structure, a lot stronger final state interactions, internuclear cascades. So we have to deal with that kind of uncertainty. But nevertheless, this kind of technology allows us millimeter scale resolution and excellent calorimetry in principle for particle identification. This is just a few examples of what those actual images look like. You can see here that you have a gap between this particular vertex, and then that's likely a pi 0, for instance, that then decays into 2 photons before showering, which is very nice. You probably have these this proton here as well, which is again wonderful to see at these, we're talking less than 50 centimeters here, which would be entirely inaccessible at other places. Now, getting to the angular reconstruction, you want to be, of course, be able to point at low energies to be able to reconstruct that baseline. And the question is how we do. We're preparing a publication right now on how well we're reconstructing our atmospheric neutrinos in Dune. And of course, the question is whether we can do better. You can see here the breakdown by true nu ECC, nu mu CC, or neutral current interactions. And you can see this is a function of different algorithms. The most energetic particle in black here is much more similar to a super Kamiokande-like interaction, super Kamiokande-like reconstruction algorithm, where generally speaking, you have access only to the lepton. So if the most energetic particle for us happens to be a lepton, that would be a 1-to-1 match. That isn't always the case, of course. Sometimes your most energetic particle might be a proton, might be a neutron, might be something else. But nevertheless, if we use that one particle for pointing capabilities, basically we would be pointing back, and you can see that at very, very low energies, we have not great reconstruction, but at higher energies, maybe above 10 GeV, we have relatively good pointing. Of course, our sensitivity to things like delta CP all lie in this 0.1 to one GeV region. And so we have to overcome that either with new methods or new algorithms. Just to kind of show you the impressiveness of Dune's technology, right, is that you can look at the black to the orange here. And this is where you actually are utilizing the particle identification capabilities of Dune, where you're able to say, this is a proton, this is a pion. I'm able to identify them by their DEDX, their DQDX. And then because of that, you actually can get something like a 10% improvement. And that's not 10%, 10 degree improvement, which is what, 5%? Anyway, point being that, of course, this changes as a function of energy, it changes as a function of the flavor, et cetera. But nevertheless, we want to ask the question, can we do even better? And this is where some of my own work is currently heading, looking at basics of machine learning and trying to understand if there's ways of physically putting information into the system to be able to get better reconstruction out. So again, we're motivated by this idea that in the sub-GeV region, we hopefully have good delta CP sensitivity. There's different interactions here. We have 1 proton, 2 proton, or 0 proton in the final state. And one interesting thing that is not exactly written in this study, but if you talk to the authors, they basically tell you that this sensitivity can get even better if instead of assuming something like 15% pointing, 15 degree pointing uncertainty, if you can get to something like 7 degrees, which is very, very hard, to be clear, maybe entirely impossible, which I might show you here. But the point being here is that if you assume that you can do this better, phenomenologically, this 3 sigma sensitivity here goes to 5. And that becomes very, very interesting from a complementarity and competition perspective with our international partners and other experiments, because Super Kinematics is still running, Hyper Kinematics is coming online, Juno is coming online. All of these are going to be measuring these kinds of effects, these kinds of PMNS parameters, and we need to make sure that we have the ability to remain complementary. And so if you start combining a 5 sigma measurement capability with atmospherics, with a 5 sigma measurement in beam, this becomes very interesting very quickly. Now, this study used primarily these quasi-elastic like CC, 1 muon coming out, 1 proton coming out interactions, as I said. So we'll kind of focus on some of those. But in principle, again, our question is whether we can improve this and whether we can use physics-informed machine learning maybe via particular choices in loss functions to do this improvement. Is that correct, by the way? Yeah, it is, okay. All right, so how do we improve this? So kind of as a toy study, the way that you can kind of think of the conception of this development is through an accelerator. So again, we produce our neutrinos. They're all coming out basically in the Z direction. Now, the interesting thing is that if you ask how most people do energy reconstruction with accelerator-based neutrinos, if they happen to choose a machine learning algorithm to do this reconstruction, which is not always the case, but it can be, what they typically do is not actually physically relevant, which is that instead of saying, I want to reconstruct the object, instead they say, I want to reconstruct the magnitude. These are different statements. These are scalars versus vectors. So the key that I'm proposing is that we not look at the magnitude of our vector, but we actually look at the full vector itself. Now, what this means, right, is that we basically break the assumption that we've not been constraining previously in the context of that we know something about the incoming neutrinos in our beam experiments, which is that they come in basically through a pure Z direction. There is some divergence, but not very much. So what we're doing at the moment, most of the time, is that we're actually ignoring mutual kinematic or angular constraints that we should have on our incoming neutrino energy. Another way of saying this that I'll show you here in a second is that basically, if we were able to have an energy estimation and an angle estimation, and if you were to have both of these predicted either together or separately, a way that you would think about this is that if I don't point back to the target, I should quote unquote reject my measurement. Now, there isn't necessarily a way in machine learning to reject a measurement or reject a prediction, I should say. But instead, what you do is you try to do a loss, a according to that. So you try to minimize some loss simultaneously instead over these different variables simultaneously. This is called a multi-objective or multivariate or composite loss function. It's not something that's entirely new. It's just something that is a little bit unique, apparently, in the context of neutrinos. So this is the basic argument that I visualized. Is that if you had two separate sets of data, two separately trained algorithms on the same set of data and you tested, basically in principle, you can have the same event come up with the exact same energy, but if you asked another trained model, I should say, to reconstruct the angle, they wouldn't necessarily agree. And so this is technically happening because we're not being limited in the way that we should be, constrained by the other parts of our actual physical object, which is, of course, the 4 vector. So the argument is as follows, is that if you want to do something like mutual constraint in this way, you want to do mutual loss, what we want to do actually is not do a loss of a single variable, but in the simplest way, we would do a composite loss of many single variable loss functions with coefficients applied. This is not something that's new. This is just a composite or multi-objective loss function. People do this in partial differential equations, all kinds of things for different applications. Now, in the context of what we want to make these physically relevant or physically informed. So what we want is to make sure that we predict what we should know as correlated variables in our physical system. So the idea here instead is that we take our, for instance, loss function of two related variables, and we make them our energy, for instance, and our momentum. Okay. Now, obviously, the neutrino is basically massless, and that should already tell you that there's probably a loss function that you should consider. But the point here is that at the moment, we can have two or many different loss functions in principle that all communicate together through this composite with coefficients. We add up and we try to minimize the total, not individual. So this has been done in principle in the past. So one particular machine learning algorithm that did this in the context of the NOVA experiment, if you've heard of that, was the LSTM neural network architecture, which basically minimized this particular loss function, where we were looking at the true neutrino energy and the true lepton energy. So this is with a charge current interaction, for instance. And so you did reconstruction, you tried to come up with an estimate for what all of your different particles were coming out of that particular vertex. And then you showed those reconstructed objects to the machine learning algorithm, and then it tried to come up with both of those, given the truth. Now, this was taken over by Xiaowei, who's at Minnesota with me, and he's now finished initial deployment and developments for basically a translation of this LSTM into a transformer architecture, which is what I've been using right now. He's also applying this to Dune and has finished application of this in Node. So this is the basic format. You have transformer layers, you have multi-layer perceptron, you have vector input and scalar input. So what this means, right, is this is like the prongs or the tracks that you would have. So in the context of Node, we call these prongs. In the context of Dune, we call these tracks. So you take a vector and you put this into your transformer layers of all of the particles that you have in the final state versus the scalar or slice level event level inputs. So if I had a total energy or a total missing momentum of the entire event, this would go into the multi-layer perceptron before being combined. So you can see code here. It is freely available and actually has a number of users already.
Yeah, good question. So how, whenever I think of these type of things or like specific models, I always wonder how good they are in terms of, you mentioned Dune and then you mentioned Nova. But then I feel like even with, when you think of Gen 4 or any generator, it tends to be really specific for whatever experiment you're in. Do you know if something like
I mean, Gen 4 is pretty universal.
Excuse me?
Gen 4 is pretty universal.
Yeah, but then you have tunes for microphone and you have
Not in
the,
Jaunt form. In Genie you do,
all right, sure.
but Jaunt is Jaunt, but yeah. There's different versions, I agree, but they're not tuned, so.
Fair enough. Fair enough. Sure. And then, but then, you know, at what point does it become, like, I wonder something like, if this is more universal, so like you take. Can you, because you're, at this point, you're doing, what you, like, just, you're getting the reconstructed. And there's so many ongoing experiments, like even just in Fermilab itself, ABC, to go down to the underlying physics, I think that'd be cool, but I don't know. if
No,
that's-
yeah, so maybe a way of, if I'm interpreting your comment right. So this is using already, if you will, reconstructed objects,
okay.
right? So what this particular network is not working on, for instance, is like the hit level.
Okay.
So I'm not showing it images.
Mhm.
So that's where potentially
Yeah.
you might be very sensitive to changes in Giant, changes in detector systematics, changes in detector simulation, changes in your underlying, maybe small changes in like your proton threshold or something, right? So that can change the number of hits, that might change the behavior. Now, in principle, what's kind of happening, right, is we're smearing all that out
Right.
with this level of input. Now, what it does show, at least in Nova, off the record, is that this is still comparable, if not better even than the hit-based algorithms. At least in the context of Nova,
Yeah, yeah.
which has other things that may give it that ability. So it's a little bit, now, this is in some respect, if you will, double counting. Because there's plenty, like in the context of Nova for sure, and growing in Dune, there's lots of machine learning algorithms that produce these tracks, that produce these total scalar, total slice level, event level outputs, right? So we're kind of doing machine learning on top of potentially other machine learned things, right? So there is a non-negligible possibility there that you get extra systematics that way. But I can say that at least currently, in the context of Nova, where he's applied these kinds of architectures, there's a way actually of getting out of some of the detector systematics errors and make it much more consistent.
Yeah.
So, and we can talk offline if you're interested. Yeah.
So I recall like from Nova, a lot of there are cuts that are based on like they have a lot more cosmics than Dune will.
Oh
have.
yeah.
So there's all these cuts.
They are also about a factor of 1,000,000 times faster though. So they have 5 nanosecond timing roughly.
I see. Oh, I see. But their reconstruction is also at the energy level, not at the kinematics level. It's like that's.
Yeah, they do kinematics. Yeah.
Oh, okay.
So that is the prong level input,
Okay.
if you will. So maybe I can skip this and
Yeah.
maybe show you like a very brief way that we do this. So like this is the kind of vector level versus scalar level. So you can think of scalars that you would want to learn from, okay, can be, for instance, the event level variable, okay? So I'll actually skip to this. For instance, the total kinetic energy, the total momentum, the total missing momentum, okay? The vector that you would also learn from would be your final state particles, maybe not necessarily your final state lepton, but in principle, you could be a vector of PDG codes that all come out of that particular event, a vector of masses that all come out of that event, and then momenta, et cetera. Is that kind of, so these are all inferred in principle, right? I can have a machine learning method that says, I think that the PDG is this. I think that the PID is this, I should say, right? I think that the momentum in the Z direction is this. Now that can be classically done as well, right? You can do that. But a lot of the time there are layers to these things sometimes in the different variables that come out of our root files. So yeah, they're all in principle combined. So the way that we do this, right, is that one of the impressive things that Xiaowei was able to do was take the LSTM architecture, convert it to a transformer, and then allow it to actually take effectively an infinite number, not infinite, of course, an unknown number of potential targets. So in principle, every variable can be predicted. So I don't have a limit on the number necessarily. So if I want to do, for instance, the energy and momentum of the neutrino, or the energy and momentum of the final state lepton to be more LSTM style, I can produce all 8 of these as targets, as predictions in principle. And then you start doing interesting things with this because it allows you to actually do correlations between them. And of course, if you're minimizing the loss collectively, that's an encouragement because that's more physically informed in principle. You know that one of these should constrain the other. This is what kind of the data inputs look like. You have, things like our targets, like momenta, but then you have cos theta, for instance, which would be like the incoming angle. So I'll just show some brief results here. This is from Ricci, who was an intern with me at Fermilab last summer and really did some great work and now is going to CERN for the next summer, which is really cool. So I won't go through this, but this is kind of what our neutrino spectra look like. This is what our proton multiplicity looks like for atmospherics. We're doing all of this in the context of Gini, which is tuned and does change quite a bit sometimes depending on the tune. But point being that here you can see different multiplicities of our final states, et cetera, different spectra, and then our angular distributions, for instance. And then what we can do on this Gini input, basically we're doing truth level input with thresholds and other kind of simple cuts to try to understand what the effects generally of the detector might be, but hopefully in a way that we can diagnose any anomalies before passing through the full reconstruction chain, where you get lots more smearing and other things that kind of crop up. So you can see here, for instance, if we make a cut, for instance, on the energy of 0.1 to 1 GeV, we allow any neutrino flavor and any topology in number of protons, in number of pions for a particular nuclear model configuration or tune. You can see some of the differences here collectively in these different spectra. If we do a loss now of these 4 different variables, we're trying to predict all 4 of them, and we constrain them against each other with this composite loss function. We can use a mean absolute error. We can do a training and a validation, of course. You can see that they're quite nicely together here. We can compare that. Is that a question?
No.
Okay. We can compare that to a single variable. So this is kind of interesting. This is more similar to what a more classical machine learning algorithm might be, right? Where you are just trying to produce just the energy of the neutrino, just one output. And what you see between the orange and the blue, the training here on the 4 momentum and the validation, is that the behavior is much smoother in the case of the multivariate case. So if you look at if you have the exact same architecture, exact same loss type, et cetera, just the fact that we're now producing more variables at once, you actually can effectively go down to your asymptotic limit faster and remain there. Unlike, for instance, in the validation case here in red. So kind of interesting. If I go to a resolution on that energy, I can do this as a function of true neutrino energy, again, in the 0.1 to 1 GeV range. I'm not looking at any cuts on my process. It can be neutral current, charge current. It can be all different types of flavors, all different types of topologies. So this is in number of pions, in number of protons, and I'm ignoring neutrons. What I see here is that I can change the different kinds of losses. If I have an energy only loss, a 3 momentum loss, or a 4 momentum loss, in this case, what you see in the green and the blue is that basically the behavior of the energy only prediction versus the 4 momentum prediction is exactly the same, which is encouraging. That also means though that you get basically the same behavior and you get pointing. Now, the kind of weird thing that you see is, of course, that you have a 3 momentum where you're training on the energy via the combination of those because the mass is 0, but you get angular information from the 3 momentum similarly. But in this case, you can see a relatively consistent bias rather than, for instance, a decreasing one and then flat. So kind of interesting differences in behavior. This is a interesting plot where you have 5 different trainings. So this is using a 4 momentum loss, using a mean absolute error, okay? Again, all flavors, no neutrons, and then we're actually cutting on different processes. So if we have a fully inclusive sample, so this is all different types of neutrinos, all flavors, all possible final states, you get the black, okay? If I train then on just neutral current and all topologies in the light green versus the dark green with just 1p 0 pi final states, I get these 2 here. So as you can see here, what that means basically is that the neutral current is very hard to learn from because there's an outgoing neutrino. I don't have an outgoing charged lepton, and I don't have as much kinematic information. And so I'm relying almost entirely on the Duronic information. So that biases things, especially in the case of no neutrons, where I'm not reconstructing those neutral particles. In the charge current cases, I can see that the NP in pi case versus the 1p 0 pi case, in the dark purple, the 1p 0 pi case, which is related to our quasi-elastic interactions, has much better resolution compared to the all possible final states case. So kind of natural behavior that we're seeing. Now, the problem, of course, comes when you start looking at correlation plots, and you see that there's this very weird bias. And this actually comes from neutral current interactions here, where we have, very diagonal behavior from the charge current. But because the neutral current is biased because of the loss of the lepton, basically with this invisible final state, right? You try to make up an energy and you're just wrong. Okay, so what this effectively means, right, at least in the context of this training that I'm showing, which we have a couple ideas of how to get around, is that neutral current just can't be treated as charge current. It's not universal enough. The architecture may be similar, but you might need to develop a completely separate architecture just for the neutral current cases, just because it's so much harder and all you're dealing with, right, is the outgoing patterns. So we're losing important information. Similarly, because of those neutral currents, by the way, you get basically terrible angular reconstruction. Now, there is a diagonal element here. That diagonal element is from the charge currents. But there's a further possible change in variables that you might want to consider. Rather than trying to reproduce the angle just from the momenta, you can change in angles, different things. You might weight the different coefficients of those different individual loss functions in the composite loss function differently. But you can see the overall kind of performance here as a function of theta resolution and energy resolution. So you can see that we have quite good energy resolution. Now this shelf is that neutral current, but of course the angular resolution is terrible. So this is exactly the opposite of what you would want to do for a delta CP measurement, right? I don't have good pointing in this particular energy regime of low sub GeV neutrinos, but instead I have terrible pointing and okay energy resolution, basically the exact opposite of what we want. The interesting thing is that if I change from a mean absolute error to just a mean squared error, I go into a nonlinear case, I actually get somewhat better behavior. So just changing the loss function type, not the loss function variables, is actually enough to give you interesting behavior. So you can kind of see this in these contours. You might say that an ideal is something like 30-degree pointing plus or minus, right? With something like 15 or 20% energy resolution. And of course, the point here is that we're getting close to that somewhat, but not perfect, of course. We have 68% in this area for the population density here, and we need to do better. You can also see that there's a lot of anomalies here, right? Because of all of the different processes that are coming in, including neutral currents. So these are theta resolutions versus true variables, angular energy resolutions versus true variables. And you can see a lot of structure, which means that there's basically too much going on. The data is not clean enough to be learned from. You need to do more about, okay, I'm going to train on this process versus this process. It's a little bit harder to do it collectively. Again, a lot of this is because of things like neutral currents. So I'll skip ahead. I know it's at time. So I'll kind of show you what happens if you instead go with effectively just charge current interactions. So you get much better behavior. Here, you're still ignoring neutrons, you're still looking at all different topologies, but you're basically looking at charge current interactions only. We have very diagonal behavior in our true versus predicted energy. You can see that in this confidence level plot. You can see, we're actually quite confident narrowly, something on the order of, 10% to 20% there across all of these different energies up to 1 GeV. That's great. You can also see that for our angular resolution, at least again here in these truths with thresholds, no neutrons, etc., where you have pretty good diagonal here, but not great. The point here is that there's actually a limit that's going to be imposed from the nuclear physics. So you have Fermi motion, you have final state interactions, all these things that make it harder and harder for us to point. We can do energy resolution quite well because we can still reconstruct the particles, but if they then rescatter on the way out, you don't have as good a pointing. So this is kind of the money plot in some respect. So again, this is the theta resolution versus the energy resolution, again in truth with thresholds. And you can see that we're starting to get interesting behavior, but we probably need to optimize more. We may need to change our loss variables, potentially add more, take some away, different kinds of aspects of our loss type. All of these basically combined just for the charge current case. And you can see that all those anomalies, given the resolutions versus true variables, have basically disappeared in this charge current case, which is encouraging. So I'll leave you with this. This is the plot that I wish I had made first and would have set me on a different path, which is we should plot the neutrino mass squared, because the neutrino mass is so small that it should basically be 0. There's other things that we're trying to minimize to 0. I wonder what they're called. Oh, they're called loss functions. You should probably just make a loss function of your neutrino mass squared because it's the physically relevant thing, which of course is related, by the way, to the relativistic formula that creates your 4 vectors. But nevertheless, because I have all these variables now predicted, I can actually investigate the structure of their behavior versus a real quantity collectively, right? I'm not just looking at energy, I'm not just looking at momentum, I'm looking at them all collectively in something I know should be physically relevant. And so in this case, you can see again, fully inclusive in black, neutral currents in green, and in pink and purple are charge current. And there's some interesting structure, which says that if you're in charge current, as you already saw, there's really nice behavior. We have basically good reconstruction around roughly 0. Now it's positive, it's not perfect, right? We get a bias, but it's something that in principle, we will hopefully correct when we actually move not just to a composite loss function of 4 different variables, but a composite loss function that actually makes them talk to each other directly. Now, this reconstructs well for our charge currents. For our neutral currents, it's not as well. That's in the green over here. But the interesting thing that comes from this as well is that you can actually kind of point to different processes turning on and the algorithm actually learning different aspects here. So you might notice down here that you have a crossover point, which is kind of interesting from this multivariate method, right? That what I see in the pink is NP and pi. So any number of protons, any number of pions. The light green is also NP and pi. But the dark green is just 1p0 pi. So it's just quasi-elastic like. The light green has the ability to have resonances, have multi-proton production, etc. And all of these turn on at the same point. So the interesting thing here in the light green, right, is that you basically are seeing probably a charge current process, a neutral current process turning on for a pion production and a charge current process turning on at the same time. And it's being learned at the same place, which is encouraging. So you actually are getting some PID without even requiring PID, which is interesting. So all of this is to say, thank you for your attention. There are some future plans, including implementing these other loss functions that are even more physically relevant. But the other thing that I'll mention is that we want to use these kinds of methods to actually produce really interesting kind of novel variables. So there's talk of trying to do better Q-squared estimation. potentially doing Bjork and X estimation, where you can do interesting stuff with either quasi-elastic physics or SRC physics or even resonant physics, where you can reconstruct these in a way that would be machine learned and hopefully constrain one against the other. And we will probably be developing a neutral current algorithm separately, but there is a question of training, which hopefully we can see what happens when we flatten these different spectra to hopefully have a more biased measurement, or not unbiased training, I should say. So yeah, I'll take any questions.
Thanks for that. We have time for maybe one question and the rest we take offline.
Otherwise, we can have coffee.
Yeah, so why don't we thank the speaker again and, oh,
You had a question?
Oh, yeah, yeah, just does so when you're making these plots that distinguish charge current and neutral current, does the model tell you whether it thinks that it's neutral current or charge current?
No, it's trained separately. But the fact that you have separation, right? So there's a line there.
It could learn that this one is.
There is some overlap, as you see, between, for instance, the pink here and the purple here for the one proton case, but there is a separation.
Because I guess if you had events and you were trying to say, do a delta CP measurement and select just the charge currents, that you have better angular resolution.
Yeah, so there is a possibility, right? Like the nice thing about these multivariate method that Xiaowei has developed here is that I can predict in principle any kind of variable. I can predict a Boolean, right? And I can put it into the loss function and I can make it work, right? I can scale it with different coefficients and make it less important, more important. And in principle, I can correlate that with kinematics, which we know in principle should be the case, at least at very, very minute levels. Not levels that you can detect in any kind of normal experiment, but the point would be, right, is that in principle, there should be a correlation with your PIDs and that, right? If I have the ability, for instance, not confirmed, but there are some machine learning algorithms which can somewhat tell the difference between, for instance, pi plus and pi minus because of capture, okay? If I'm able to identify that there's a single pion production, and I'm able to say that it's a pi minus, that is more likely to come from, I believe it's a nu bar anti-neutrino interaction. I get them mixed up all the time. Sorry if I mixed it up. But the point there, right, is that in principle, there are these ways of separating those kinds of interactions. The same thing with, if you're able to identify high energy neutrons. There are some people in microboom who are able to do this now, right? Where in principle, you have higher confidence that the interaction might be from an anti-neutrino, because only neutrinos produce final state particles that are protons, at least, unless there's charge exchange and other stuff that happens in the final state interactions. But there's lots of these kind of separations that you can do. So we do have convolutional visual networks that work on the hit level, not the reconstructed object level, that are able to do this kind of distinguishing, where you have different nu e, nu mu, nu tau, neutral current separation capability. The interesting thing is that I haven't done the exercise that I want to, is that if I make an integral from here to here, and then here to here, I'd like to know what the ratio basically of neutral current to charge current is. Currently, our efficiency for identifying neutral current in most CVNs is something on the order of 70 to 75%. That looks kind of similar to me, which is really weird because I didn't tell it anything necessarily about it, right? And all I have to do is drop a line using pure kinematics and I can get it. Now, I'm not saying that it's going to be as good, but the fact that it's even similar is interesting. So yeah, it's a very adaptive, very flexible network. And, you know, I can, for instance, the other kind of nice thing that you can do is you can even carry around PIDs. So one thing that's kind of difficult with some machine learning algorithms is that because they're producing really one variable outputs, they're kind of black boxes, right? But if you have these composite loss functions, if I have a loss with a coefficient plus a loss with a coefficient plus a loss with a coefficient, right? I can just turn the coefficients off, but I keep the losses. So I can carry around information and correlation for my final state outputs that doesn't require to do me any kind of index matching. So that actually opens up the box a lot more compared to your testing data and your training data simultaneously. So you can do interesting things like that where you're predicting junk, but it doesn't affect the loss. It doesn't affect the minimization or optimization process. But yeah, it's in principle something that we can do with Booleans. So it's kind of cool.